Far beyond the familiar twinkling of our night sky, there lies a rugged alien planet. But what's this? For a moment, it seems we have indeed discovered an alien being. Yet, upon closer inspection, it is not an extraterrestrial creature at all, but an earthly octopus.
Thank you, David, for the introduction, and welcome everyone to my presentation, Octopus Neuromorphology and Optimization. Today we're going to dive into the coleoid cephalopod's journey to cognitive complexity, the anatomy of the octopus nervous system, and how they are perfectly adapted for the environment in which they live. So sit back, relax, and I hope you enjoy the presentation. Grasping the complexity of an octopus's nervous system requires a deep dive into the cephalopod's evolutionary journey and lifestyle history. Coleoid, that is shell-less cephalopods, including octopuses, squids, and cuttlefish, all evolved from a common ancestor, likely something that looked like this, a nautilus. The question arises, why would they lose a shell? Is it not beneficial for their survival? The reasons behind the functional loss of the shell are still being debated. However, Packard's theory states that competition with pelagic fish forced ancestral external shelled cephalopods to venture into increased depths to acquire food needed to survive and avoid predation. The subsequent increased pressure in these environments caused drastic shell reduction or even complete loss in some species. Other theories for their divergence into the depths suggest that as tropical waters disappeared in the Ice Age, the cephalopod ancestors had to venture into cooler waters below. Below 600 meters, the temperature rarely fluctuates, providing a sanctuary for their species. In these new depths, a new era of cephalopod species began to emerge. No longer constrained by their hard shells and living in a stable environment, evolution was allowed to run wild. Hundreds of cephalopod species emerged, all different from each other in various ways. Adapting to life without a hard shell, the common octopus shifted to a benthic lifestyle, diverging notably in body plan, anatomy, behavior, and intelligence from its other cephalopod counterparts. By adopting the seafloor as its home, modern octopuses face new evolutionary pressures compared to their pelagic cousins. The hunt for food was now within the nooks and crannies of the reef and rocks, the same locations that octopuses rely on for protection from predators. Traversing the ever-changing and complex benthic environment required a larger brain to face new problems and body structure modifications. Most likely, the benthic cephalopod ancestor looked something like this, a Dumbo octopus. As the Ice Age came to an end, they would have migrated back to those tropical shallows with the warming of the waters. With the common octopus that we see here, successfully using those adaptations it evolved in the depths to create a new life in the shallows, and throughout time, creating the modern octopus that we know and love today. Now, not all shallow water common octopuses exhibit the behavior that you're seeing here, but it was a unique one that I wanted to include in my presentation. Now, let's move on to the anatomical layout of the octopus nervous system. The figure that will come up on the slides next represents the general structure of an octopus's nervous system, excluding the optic lobes. This system is anatomically divided into three interconnected parts: the central brain, the optic lobes, and the nervous system of the arms. The brain and optic lobes comprise the central nervous system, and the arms are the peripheral nervous system. The central brain and optic lobes are pivotal in sensory processing and decision making, while the peripheral system governs an intricate array of motor controls. So as we can see in the figure in the bottom right there, the peripheral nervous system is used for contraction, elongation, and bending of the arms, versus the central nervous system is for arm coordination, so when acting as one big unit, that includes grasping, object positioning, the sucker use, and reflex. It's important to note that the central nervous system still plays a role in arm coordination, maintaining the capability to orchestrate total control when needed, such as jet propulsion, swimming, or purposeful navigation of the environment. Uniquely, around 300 million of the total 500 million neurons lie in the arms alone, with the remaining 45 million in the central brain and 160 million in the optic lobes. This means that the neurons in the arm comprise approximately 60% of all neurons in an octopus's body. This layout means that the peripheral nervous system is functionally independent from the central nervous system, and each arm can work autonomously in a live octopus and also in an octopus that had an arm severed. This is illustrated by the fact that a severed octopus arm can respond in the same manner as an intact arm with general stereotyped movements. Key to the octopus's sensory abilities are the specialized tactile receptors, also called CRs, and they're located on the suckers in each arm. These CRs are fine-tuned for a taste-by-touch mechanism. This allows the octopus to sense its environment and detect prey. Even when they can't see it or interpret it with their central nervous system, they're actually able to taste. So as they're going through the environment, looking through the cracks, looking for prey, they're tasting as they go along. And when they notice something that they like the taste of, they'll actively pursue it and engage in predation. Speaking of predation, it appears that this octopus has found something that he likes, a crab. Now is a great time to move on to the next section of our presentation, the adaptive strategies and habitat mastery of an octopus. Here we're going to take all those anatomical features that I described before and discuss them in the context of behavioral adaptations. Now, despite what you're observing in this documentary, octopuses do not tend to hunt by sight, rather employing a stop-and-go strategy. We'll discuss this in a little bit. For now, let's talk about habitat mastery. Anyone who's been scuba diving or snorkeling knows how complex and convoluted a reef is. Not only is it hard to see your prey, but it's also hard to access them in the tiny areas that they might be hiding in. This is where that advanced peripheral nervous system comes into play. Each arm acts as a semi-autonomous hunter, relaying critical information to the central nervous system. With the layout of those neurons in the arms and the chemotactile receptors, the octopus's nervous system has thus evolved remarkably to thrive in these intricate environments, effectively hunting their preferred prey. This figure illustrates the vast range of environments octopuses inhabit, as well as variations in the organization of their central brains. The light blue area, which is the vertical lobe, and the dark blue area, which is the medial superior frontal lobe, are both regions that process visual information, while the green area, which is the inferior frontal lobe, is dedicated to tactile processing. As we can see, octopus species in shallower waters exhibit enlarged visual and tactile sensing areas compared to those in pelagic and aphotic zones. This enlargement likely results from the environments being more physically complex, as well as increased light availability in the shallower habitats, necessitating enhanced visual and tactile processing capabilities to be successful in their niche within those habitats. Now, to talk about hunting strategies, we will look at a study that I discussed in my paper. In this study, octopuses were observed foraging in daylight hours over a 6-day period in French Polynesia across coral reefs. Employing a stop-and-go strategy, as seen in the video above, foraging was exclusively tactile and speculative. The octopuses either pounced on suspected food objects or probed through rocks and crevices for prey. Not once was a visually guided attack on prey observed throughout the entire study. Every instance of predation began with tactile contact, eliciting a reaction from the entire organism to successfully capture the prey. The study concluded that visual information predominantly aids in foraging path selection, predator avoidance, substrate recognition for crypsis, and den navigation. Summarizing what we talked about today, evolutionary distribution was critical in the nervous system development process. The anatomical layout of the octopus nervous system is unique for their niche. Each arm is a semi-autonomous hunter, capable of touch and taste. The central nervous system can have different layouts depending on the habitat. And finally, to complement their anatomy, they employ a stop-and-go hunting strategy. On that note, I'll pass it over to David for a final send-off.
As we conclude our journey into the fascinating world of the octopus, we are left in awe of its complex nervous system, a marvel of the natural world. This remarkable creature, so alien yet so familiar, challenges our understanding of intelligence and consciousness in the animal kingdom. It is a vivid reminder that on our own blue planet, there are still many wonders to explore, understand, and marvel at.